Welcome to lesson 7 of the data handling and machine learning course. Today's topic is time series. And our 3 sections that we'll have is first plotting of multiple time series, second filtering in the time domain, and finally a brief introduction to the Fourier spectrum. We have seen how to import data, how to handle data when they come as a Panda data frame. But now we are mostly using what's shown up here behind me. It's NumPy arrays. And so it will also be a bit of a practice into handling NumPy arrays today. To make things a little bit quicker, rather than me typing everything, I copy and pasted a couple of things like the read CSV, the subplots, and a couple of NumPy functions. Okay, so then I have prepared a data set, which is the same data that you use when you go into the lesson materials. So I'm not doing any different data sets. So if you have the lesson materials and the downloaded data folder for that, this is what I'm going to do now as well. So let's just have a look and see a couple of features that might be of relevance. So I use read CSV to import the data, and they come from a txt file, text file, just plain ASCII, just numbers in there. And there's a specific feature, namely those numbers from the clinical recording machine where they are taken from were actually saved by numbers separated with just spaces. So there are no commas between the numbers. And incidentally, you can use read CSV, although it says comma separated values. You can also use it for reading space separated values. And the way to do that is to set this keyword argument delim whitespace to true. So whitespace is just a blank space between the numbers. But of course, you need to be sure that's actually consistent throughout the data set. So then we have a data frame, and after that, I specify 2 numbers. So when we deal with time series like today, the meaning of time series is that you have the data as usual. You have rows and columns in the data frame, but there's a specific feature within the columns, and that is the sequence within the columns. So the sequence of data points in rows, along the rows in one column, is defined by time. So it's a consecutive sequence. It does make a difference whether one data point in row comes first or later on. And so to preserve this, we are also always interested in what is the time scale of the recording. Of course, can be anything, but we have to somehow define that. So here it's defined for us. It's written here as a comment, it's seconds. So whatever we're dealing with below is expressed in seconds. So if you want an interpretation, you need to interpret seconds to it. And the way to provide this information to sort of your code, such that everything is put out in seconds, is to define the sampling rate. So with every time series, there needs to be a sampling rate or an equivalent way of telling you what the difference between 2 data points means, how much time has passed from one data point to the next. So hopefully it's equal spacing, and then everything is easy because then it's a consistent time stepping throughout the data set. If it's inconsistent, there are some additional troubles, and you might want to switch from a pandas data frame to actually a pandas time series, another type of object that is able to deal with those special things. But for us, it's not relevant. You do that if you are into time series, you can do these things. For us, just the data frame will be enough. And the sampling rate is nothing but telling you how many samples were taken per the unit in the defined time scale. And if we have seconds, then a sampling rate of 256 tells us this data consists of 256 recording or points or rows per second. So if the data are on the time axis arranged in rows, then 256 samples or rows comprise 1 second. And the next is the duration. 5 seconds means how long, how many rows do you want? And you just multiply the sampling rate with the number of seconds that you would like. So 5 times 256, what we're doing here, gives you the number of rows that you need to read in for a data frame to have 5 seconds. Right. So that's it. It's almost it, not quite. So then, as I said, we're going to use NumPy arrays so we can convert this whole data frame as is defined here as df into NumPy array, df sub np, just for abbreviation. But then I actually make a selection of the data and put that into a variable called data, just a generic thing. Then whatever you import, it's just called data later on, and you know what it is from this import. If I execute this code, we can have a look at the data frame head, which means we can have an overview of what's contained. So we see the rows here numbered by the indices in the first place, then some numbers that go from, I don't know, minus 100 to plus 100. I think the values represent here, that's electroencephalogram, represent microvolts. So voltage and microvolts is the signal that you get from the human brain. I'll explain in a second. The columns are called FP1, FP2, so that stands for frontal polar 1, frontal polar 2, which is frontal polar left, frontal polar right. It's just a convention to name electrodes posited on the scalp of the brain. And then F is for the frontal lobe, so somewhere here, then central part, parietal part, and occipital part in the back of your skull, just indicating the location where recordings were done. And the interesting thing here is that this data frame contains many things that are for our purpose irrelevant. So what I'm doing is I'm just telling you, please select the most interesting features that we want. And by features, we mean columns. And so everything from A1, A2, which are reference electrodes, which are not interesting for us. EKG, that's German for electrocardiogram. So it was recorded in a German hospital. ATM is for Atmung, that's respiration. So all things that were in the clinic recorded at the same time to have a more complete picture of brain activity, which I don't want to go into detail about. So we're making a selection. And from the NumPy array, you know how to make a selection. You slice into that array. So we start from, when it starts with a colon, it means start from 0, index 0, and we go up to durations times SR, which you might remember is the number of rows to have to be needed for 5 seconds of recording with that sampling rate. And we only take the first 19 columns because this is what we call the EEG, the electroencephalogram. So human brain activity recorded, in this case, a child of, I think, 11 years, if I remember correctly, a male patient, 11 years, and with a history of epilepsy for a couple of years. So that's what it is. It's from a pediatric neurology station, and we're just looking at some of the data later on. And yeah, you can see from the header 5 rows, 28 columns in total. And if we select the first 90, we only have the voltage recordings of brain activity, presumably due to neural activity. So it's, of course, recorded at some distance. You put it on the skin, the S is the sensor on the skin here, but assuming that the skin and the hair and the scalp and the membranes that encompass the brain are not creating extra signals, then this is mostly neural activity recording, albeit from a distance, and therefore an integrative measure, large numbers of neurons measured collectively at the same time. Right, so that's our data frame. And the first thing now, our NumPy array is called data. So of course, as usual, and that should be a routine for you as well, we'll check It's 1280 rows, 90 columns. So it's good we know what the shape of the data frame is. And now we look at a plot of the data, and we want to see the whole electroencephalogram, so the whole data set or the data array here, in this case, plotted. And what we'll do is I'll import code of a function. So it is called plot series here, included in the file that you can download, as I pointed out before. So it's a Python function and is the way to use it. I've copied and pasted the code here. Once I have the code, highlighted the cell, I just execute that cell and nothing happens. That's good. That means the function is now known to my script or to my kernel, and I can use it. So the way to use a function is to go back and to look at the very first line, where you can see a couple of features. Def, the keyword def, definition. So it's one way of creating a function in Python, and it's used by using the keyword def, followed by the function name. I have given it the name plot series, so short for plot my time series, please. And then in parentheses, you give two arguments, which is one, data, the data NumPy array that we want to have, and SR separated by comma, the sampling rate, so that the plotting program knows what is the time scale of the recording. And the way to use this function, to make this very short, just copy and paste this piece of code here. So the name with the input arguments, and then you just put it here in a new cell. I just say plots here. So that's the function call now, as we are used to, like we have done numerous times before. And we provide two arguments. First is the data, and second is the sampling rate. So in this specific case, it's got the same name. So data internally in the function are called data, but also I have named my NumPy array data, right? This is coincidental. It doesn't have to be. So you can call within the function, this can call whatever you want. This can be called data XYZ, and then you use it within the function as data XYZ. I just used it for simplicity here. And so I can also now use it outside, because externally I have a NumPy array which is called data. So we'll have a look at it later. These are two entities outside of the function and within the function. Variables are normally not communicating except for function call and function return. And the other thing that we have defined is SR, which is just a number that we defined before. It's 256, and it's used as this number in the function code. So this is the function call, provided two arguments that should actually give us our plot, and it does. Just scroll down. It doesn't say seconds, but 0, 1, 2, 3, 4, 5 is the 5 seconds that we actually selected initially, and the function automatically put those numbers and called them time. It doesn't say seconds because, of course, it doesn't know seconds. It just knows from the sampling rate how many per unit of time, right? So if I want to have seconds, time in seconds or something, I need to add it, or I need to instruct the function that this is what's happening here. But this interpretation is then an extra step. So what we can see that horizontally, you understand already, is the time, that's 5 seconds, and vertically on the vertical axis are plotted one after the other the time series or the data, the potentials that were recorded from that patient. So brain activity, in this case, normal brain activity in a 10, 11, 12-year-old child. So there's nothing very specific here, but this is what it should look like. So what we are going to do now is we are trying to see, so it just works, right? Because the code was defined. We'll have a look at the code in a second, but let's now have a look at how to define a function. So you want to learn that because it will be extremely useful later on when we do machine learning. We'll create our own functions, or we use multiple functions. And of course, once you're doing your own investigation, you might have ideas for your own functions. So you want to know how to do that. And here's one way of doing it in Python. So let's create a new function, right? Let's say this one. We can look at it later, but let's create our own function. And what we want is the same thing. We want a data frame that we get in, and we want that data frame plotted in the way that we just saw. So let's do that. Let's program it, right? We've done enough of interpretation. We've done enough of introduction to Python. We can do it now ourselves. So I call it myplot1, and I want as an import data. So I've given it a function name after the keyword def myplot1. So that's my first plot that I define. It's call it 1 because just in a minute we'll have myplot2. So we want to expand it and make it more comprehensive. Otherwise, the 1 is not necessary, of course, so it's just there because we're going to do a sequel. Otherwise, just an intuitive name is good. And data is what we want, namely our NumPy array that comes in, the time series from the recording. And that's almost finished apart from the colon. We use that from conditional statements, from for loops, and so on. So we want to now define what should happen to, and the only thing that is known to the function so far is data. What should happen to the data such that we can make a nice plot? So what we'll do here is we'll actually go up and we copy this import thing. So the first thing that we want to do in our function, in case the user hasn't done it, so we get ready for that, we say, please import subplots, which is the way to make a plot, right? So we can do that within the function. We say, whatever you did outside, I don't know, but when you come to plotting, you need to have subplots available. So let's put it here. And then you remember some way of creating a figure environment, defining an axis, and getting that from subplots, and that's already set up. So I don't use any further keywords here. And then once you have the axis, you can use the axis to plot. And the only thing that you know is data. So why don't you plot the data? And if that is our function, if that is now all complete, just plot the data, then we don't need to say anything else in this case. And our code would be sort of finished, because then if you execute this, if you call this function, it would then make sure you have subplots imported, you have a figure created, an axis system, data plotted, and that's about it. So if you want, you can also include print finish or something, so you know it's finished, but it's more of a cosmetic thing. So let's just define this function, and you can see it's accepted. There's no grammatical, no syntactical error here. There might be a complaint. So if I forget to close parentheses and I try to make this function known, it will tell me that there's something wrong. So also it's a sort of a good sign. If nothing happens, it means the function is accepted. No syntactic error so far. And the way to use this function, you remember from before, just copy that part with the function name and give it a proper argument. And in this case, myplot1 data is the function call with the data NumPy array that we defined. And it works, right? I call the data and it plots the data and everything is wonderful. Well, sort of. So what you can see is that there's plotting here as a time axis. It's, as you remember, it was like 1200 something points. So all the rows have been plotted. And then you have a y scale minus 100 to plus 150. These are the microvolts that we obtained from the electrical recordings of that brain activity. And being 5 seconds, you can say that somewhere in the middle is 2.5 seconds. So you can about estimate what happens in 1 second of brain time in this case. So this is, of course, good. Let's now try to improve that. let's try to improve and make a plot that actually separates those columns from each other as we've seen it in the above function, without looking at in the above function, just trying to think of a strategy. Can we do it? Can we actually program that? So what I'll do is here, I'll just copy that function call 1, paste it down here, and call it something different. So I'll call it myplot2, sort of now our improvement. You could also put it on version control system as a new version of that same function. Right, so now we have an improved version, which is myplot2. And that, what do we want, right? That's the thing that we want is that the data are plotted, every column is plotted, all rows are plotted, but not on top of each other, but somehow separated from each other such that I can see them individually. So let's do that. Let's try to do that, and let's see how we can do it. So what would you need to know? So first of all, you would need to know, if you want to go vertically, how many columns are there, right? So you can define that. Columns, and how do you get it? Well, you get it from the data. If you have data there, then the shape gives you rows and columns. How many columns do you have? It's index 1. Data shape index 1 is the number of columns. I can also call it number of columns. So that's what we need. This is some information that we need, because it's the difference whether you want to plot 2 time series or 200 time series. So here is a variable that helps us do it. So what we'll do is we'll now try to offset each time series from the previous by a certain distance. And how do we get an offset? Well, a simple way to get an offset is just using integers 0, 1, 2, 3, right? Consecutively rising integers. We know how to get integers. So we create an offset. And if you remember a range gives you as many integers as you have specified. So if you specify the columns that we have, so it will give you as many integers in ascending order as you have columns in this case. So that will go, if we had, what did we have? 19 columns, that will go from 0 to 18 in index and give you those numbers. So now we have sort of a series of numbers that we can use to offset every column from the previous column. And let's do that. How do we do that? So it's a very nice feature of NumPy arrays as well. We can just add things together. So remember, we have data, and from the data set in parentheses, we have all rows, column number 0. So what do we want for column number 1 to happen? We want column number 1 to be sort of above or below column number 0. So what we could do is we could offset it by, so we could use column number 0 and then offset column number 1 by, say, some factor, say 1, right? So 1 will then make sure in the NumPy that all rows of that column will be having added 1 to it. So they will be larger. And that's actually what we want. Except we want that for every consecutive column to be a larger number. So the first is 1, the second is 2, third is 3, and so on, added to them such that they be offset more and more. And yeah, we have created an array that contains this, which is called offset, which is 18 numbers from 0 to 8, 19 numbers from 0 to 18. So what we can just do is we can just offset it like this. Plus offset will, and then of course all the data, because that's now 19 offsets. We also need to provide 19 columns in the data. So let's check if we have done everything right. Let's call this function here, which is called myplot2. Again, using on the data frame that we did before. And this is the result. So I don't know if I scroll up, I don't know if you can see any difference at all. If you can see any difference at all, that's wonderful. I don't see very much, but the reason we don't see much because the offset is very small, right? You remember that the original data were on the order of -10, or was it minus minus 100 to plus 150 or so microvolts. And so these numbers are, of course, not offset very much by an offset that goes from 0 to 18. But what we can do is we can increase the offset by multiplying it with something, say offsetting it with 10. And if I then call the function, you can see now it's a little bit offset. So let's just make it 100. Call the function again. And now we're getting nice spreading. So let's remember number 100 because that already looks quite nice. And if we keep going like 1,000, execute the code, then you can see it gets less nice again because now we're losing resolution. And if we do 10,000, I think essentially we're having straight lines. So again, like we've seen that previously, the way you plot things, of course, depends on parameters that you choose, and you have to choose them wisely. So I don't go into that. Just 100 was a fairly good number. So here we have a nice code. There's very few lines, right? Very little that we did actually. Apart from that import, the only thing that we did define columns and offset, and now used this offset to actually create a nice picture to it. So if you want, you can also improve things by saying you need to pass the that factor here because it's variable as an argument to the function. So you can actually do that by specifying a factor here. Factor. And instead of multiplying it with this arbitrary number 100, saying use the factor. Right, so you have a new function. If you now call it, you get an error. It says, oh, actually, this function requires 2 input arguments, and it's not a sampling rate, it's a factor. And we know what factor means in this case. So we now need to call it and say, give 100. So we do 100, and then we can have the same plot. That's very easy to do, and depends on you how you define, because you want to have as generic as possible that thing. And for example, this will increase flexibility. You can also try to determine the factor automatically, but that's then more into the details of the use of this technique. Right? So we have it. I don't go into any more interpretation, just to say that the waves look different depending on where you record them, and you have wiggles that are well visible in this case, like on the order of 5 seconds. And if you are interested, the colors, they come from a default. Obviously, I haven't defined the colors, so they're coming from a default. And if you want to know the default, you go into this is matplotlib colors. In the matplotlib documentation under colors, it tells you what is used if you do multiple plots. What is used by default by Matplotlib is the Tableau palette. So this part here, I can't really highlight it, but you know where it is. The Tableau palette is the colors that are used. So you can see it starts from blue, followed by orange, followed by green. And you might recall that because we have used Matplotlib very often, you might recall that the first plot is always blue and the second plot is always orange by default. So that's what's being used here. And you can also see by this, knowing this, now you can see that the first time series that is plotted, or the first column, is actually the bottom one, the one around 0, because that's the one where 0 is added to it. And that's the one where the first Matplotlib color is applied. You can also see that there are only 10 colors. So after 10 columns, then this color scheme repeats. So then it's again dark blue and orange and green and so on. And because we have 19, we have no further repetition of that cycle. Good. So we have imported a time series. We have seen the importance of sampling rate and the time scale. And we have seen how such a generic thing like a plotting function can be done easily with the definition def keyword in Python. such that it can be reused, because once you have made this function known, now you can use it as often as you like in that code. And you have seen me already referring to it repeatedly. If you change something in the function, you need to execute that function again in order to make it known. Otherwise, it's then available for later use. So that's very convenient. The more generic the task is that you want to have, the more likely you are to be well advised to create a function. So we'll do another function, which when it comes to filtering in time series filtering is one of the most important techniques of all. And so we'll also use function definition for that, but definitely also a plot of the data is something that you will want to have custom made once you're doing it a little bit more advanced than just using the defaults of matplotlib. Right? Good. New notebook. And after this introduction to plotting of time series, and the case here was, of course, multiple time series, let's now have a look at how to filter or modify time series in order to learn a little bit more about what they contain. So I'm lazy again. I copy and paste code that you can download from the web page. And just what we had before, just copy and paste that again, see if it works, make that known. And here's our data frame. Data shape, it's called data, and I've used 4. Why have I used 4? Oh, I've just used 4 columns. So otherwise it's the same, but I have now restricted the data numpy array to the first 4 columns, just to have not too much to deal with, to have a nice overview of what is, of what data features there are. So the first thing I'll do is I'll copy and paste that function again, plot series. So that was the predefined plotting function. You can also use the one that we just used. And I'll now copy a new function, and that is the filter. So we have that function known. That's the plotting function there. And now we're going to look at a new function, which is called data filter. Of course, I don't know how much you're into this, but filtering means take certain components of a time series away, suppress them or enhance them, or both at the same time. And we want to have a function that filters our time series set up such that we have every column filtered independently of the others. So apply the same filter to all of the columns in the data frame that I provide you. So this is now slightly technical, but I'll show you some features that are new compared to what we had previously. So the function definition is typically followed by a comment. And a comment with 3 apostrophes or double apostrophe quotes is meant to be is a comment. So it's not executed as a code. It's supposed to follow the function definition immediately, and it's then part of the documentation of the function. So documentation means here we have default filtering of multiple time series. So a very quick description of what it does. So it filters the time series. We'll see the result later, so you understand what that means. And then we have 2 things that are going to be used, a low cutoff and a high cutoff. And it tells you some details what it is. The filter can then be applied. You can then define what you want to have excluded and what you want to have included in the result after applying the filtering. So the idea is, of course, to take some components away, leaving others and making their features more visible. So, and then it says, I expect an input argument data, and data is supposed to be a NumPy array of dimensions n times m, where n are the rows and m are the columns or channels of recording. And SR, I need to know SR. We remember that from before. That's a sampling rate. And this is, of course, to make the function familiar to the time scale at which the recording operates. And now a new feature is now that this function returns something. So if you call this function, you'll get something back, not just the plot, but you get some actual values back. And the values that you get back are the filtered data. So something that is the same shape as the original data that you showed me, but now filtered by the specifications that you provided. Okay, then we need to set a couple of things. The low stands for low cutoff. So that's the part where you want slow frequencies to be cut off. So slow components like drifts that you don't want to see. So what is the first frequency that I want to see? Frequency specified in cycles per second. Hertz is cycles per second. So in this case, appropriate for EEG. And then you can have a high cutoff. That means you take off high frequency noise. So if the data is not very clean, but if it is noisy, then you can take off that high frequency component if you like, and you can make sure which frequencies are included, which are excluded by setting a value. So this complicated thing here has a very simple origin. There's a theorem that the highest frequency that you can get is restricted by the so-called Nyquist frequency. And I don't explain that, but that's applied here. So the Nyquist frequency is sampling rate divided by 2. And I add a very small number to it, because if I set it to the Nyquist frequency, the filter will give me an error because that's the highest, but you don't want to allow it. So I add like some epsilon, and it will still return me a sensible thing. And then I don't go into the details here, but you can look that up carefully. It's also described in the materials. You have to sort of prepare your filter coefficients and then go on the data and time series by time series, apply those coefficients, and you return the filtered data set. So you produce an array which is called data subfilled in this case. And that data array, which are the filtered data, is then returned. So remember, I said that things that are defined within the function are not known to the outside script. Well, not known unless you pass them. And that's what we are doing here. So forward here and backwards is not known to the script outside of the function, but data filled will be known, because once you call that function, you will return it or you will get it. Good. So we have a couple of new features in that function. See if we can make it known so nothing happens, so probably syntactically okay. Now, how do we apply this function? The same as before, just copy very lazily. Just copy that piece here, data filter, argument 1 data is the NumPy array, and SR is the sampling rate. So if I just do that, I get loads of numbers. Why is that? Well, I get an array, right? It says here, return data field, so I get the filtered data. So of course, that's not where I want to leave it. I want to actually call that something, say data filtered. Still something missing, filtered. I want to call that data filtered. And now I see nothing. But of course, I can now check that data filtered, which is now known, has the right dimensions. And if I check the shape, it's 1280 by 4, which I think is the same as the original data, which is 1280 by 4. So the filtering does something to the data, returns the numbers, but doesn't affect the shape of it. And so on. I have now created a filter function by executing that code. I have called the function, assigned it to a variable, and this variable is now a NumPy array that I can work on. So let's see, what do we have? Which function do we have predefined? At the top, we have plot series. So let's use now the predefined data plot to check what we got after filtering. So I go to the end. So let's do data filter data. What did that do? Took the data, plotted them. No, that's not data filter. What was it? I copied the wrong thing. So what I wanted was not the what I wanted to see is the plot. I wanted plot series, right? So let's do that. So now I'm going to do plot series, and I want to do that on the data with the sampling rate there in order to see our original data. And then I copy and paste the code, and I do another function call. Now we have, what do we have? Data filtered. So we have just returned from that call to the filter. We have received data filtered. So I can then plot this by applying the function plot series to the new data set called data filtered. Execute it and see the result of the first function call is the original data set. Looks like this. And then if I apply to the filtered data set, looks like this. Can we see any difference here? Not really, right? That looks very similar, although not the same. So if you look very carefully, we just make it smaller for the moment so we can see two plots, that the plot above goes a little bit up and down and has sort of this low, slow component here, whereas the plot below is more even. And of course, we can get this much nicer if we just say, just play a little bit with those numbers. So if we make a low frequency cutoff at 10 Hertz, if we allow everything up to 10 Hertz not to pass this filter, so we cut off everything up to 10 Hertz, make that function known, and then create filtered data, plot the thing, then we can see that now the data look very different. So this is now the filter, namely all the slow components have been taken away. Right? The slow components, those ups and downs, like the blue curve or the red curve makes here. So then on the average, it moves up and then sharply down and then up again. And this has now been taken away, leaving now enhanced all the higher frequency components of that data set. Right, so we have that in the materials. It's more to practice on, specifically have a look at the epileptic data that are provided there, which I'm not going to use now, but you will see many more features. And again, you can see that, of course, this filter function now is very simple. I just wrote something, but if you now want to go into further research, using more complicated filtering or different kinds of conditions, then it will be up to you to make a function that is as generic as possible while doing exactly what you want. Yeah, and the otherwise the important result is that the human brain signals have many components, so have contributions from changes of signals, slow components, which were more easily seen in the unfiltered data, like some up and down in the recordings, and also some fast components, which are much better seen in this filtered plot here, with only shown the high frequency components, only the fast components. You might even guess just visually that also among the fast components, there are some that are very fast. So like you can see, it's darker here at this beginning here, and there are some that are not so fast and in between. So there's a big variation in content of this signal, which picks up, of course, the activity of many different neurons simultaneously. And let's just have a quick look at a feature that actually allows you to quantify what I've just said, sort of qualitatively from looking at different plots of the data. And that is, how can we quantify the content of a time series in terms of its fast, slow, medium components just in one go. So I copy the functions. Here is the same as before. The import of the functions. I copy the reading of the data frame, which is the same as before. And we have 5 rows, 28 columns. And if we look at data following this code that I copied here, we have now extracted 2 columns. The first 2 columns, so index 0 and index 1. Otherwise, it's 5 seconds as before. And everything else is the same. So 256 samples per second, 5 seconds of duration. It's a NumPy array, and the names of the columns are all identical. For brevity of explanation, I copy and execute the plot series code. So we want to have plot series to be able to see the data. Well, why don't we apply it immediately and see what the data look like? So apply that to the data. Here's what the data look like. So these are now 2 time series. I've only taken channels 0 and 1. And these are taken from a different file, not the normal brain activity, but the epileptic brain activity. It shows us during an epileptic seizure from which this child suffers, and that's why it's in the clinic. The activity of the brain potentials looks different, right? Qualitatively, at least different. And that we want to now be able to have a quantitative tool to say what components are in a given signal, such that we can compare whether it's more like the normal that we saw before in the original time series plot and the filtered data, or whether it's more like the epileptic, an example of which you see here. So what we do is, for this purpose, we import a function. Where is it? I have imported it without telling you. It's an import of a function called FFT. This is the fast Fourier transform, and based on the Fourier theorem, which is a mathematical theorem that helps you to translate every time series that has certain features into a set of components that build it up. So the features that you need in order to apply this theorem is the time series needs to be infinitely long, and it needs to be 100% stationary. If that is true, then the Fourier theorem will apply 100%. So our time series is neither infinitely long nor is it stationary, but we'll still use it as an approximation. So it might not be the truth, but as an approximation to estimate the content of the frequencies that actually compose that signal. And so let's do that. Let's try to apply. Now we have that imported all. We see the time series. Let's now try to apply that function called FFT, which is an implementation that sort of from a computational perspective is extremely fast Fourier transform. That's why 2F. And it's just a function called FFT. And the simple thing is you can just apply to data and it will give you the Fourier transform of every column in that data set. If you specify that you want to have it evaluated over the columns, right? So you want to have data along the rows. So we want to have a Fourier output for every column. And you do that by specifying a keyword feature, which is axis. Maybe you remember from correlation coefficient. It's the same thing here. So this means you do an evaluation along for every column, taking all the rows available if you say axis is 0. So axis 0 is referring to rows. You do the spectrum along the rows. If you do that, you can create an output. So data FFT made just for intuitively see that's the Fourier transform of the data. You get it. And let's see, as a first thing, data FFT, the shape that it has. And we have seen those numbers before. 1280 is our 5 seconds. And you remember I said we only select 2 columns, so these are the 2 columns as well. So for every column, we get the 1280 so-called Fourier coefficients. Now, Fourier coefficients are nothing but telling you which frequency is there and which frequency is not there. So the Fourier theorem actually is nothing but a model of the data, which assumes that as given time series, so the ups and downs of some temporarily changing variable, can be reconstructed by using sine waves, perfect sine waves of a given frequency. And the coefficients that are mentioned, or the numbers that are actually provided here, are nothing but the amplitudes of those sine waves. Right? So if you have sine waves that you can put together, add them together, and then you will get your original data back. So it's the model that recreates the original data. Then the coefficients that are here is only telling you how big does every component need to be. So let's have a look at this. And I think for brevity, I don't go into the details here. I'll just plot it. So what I do is I need to define how many rows. I need to know how many rows there were originally, from which I can, by some very simple arithmetics, calculate the frequency in cycles per second, from which I can get the amplitudes, which I get, of course, from the Fourier coefficients directly. But if you look at it, the Fourier coefficients are complex numbers, so I need to take the absolute value, which is here, only take the numbers, the real numbers that tell us how big is that wave, and then I can plot the result. So this is our result then. I have taken the signal that looked, if I just scroll down, in the time domain, as we say, as a time series like this. So 2 channels that sort of go up and down, so that the slow up and down, and then the spiky thing here in between is called spike wave in neurology. And both have a very similar thing. So if you actually look at this Fourier spectrum here, and I think I want to zoom in a little bit. So if we just discard all the right-hand side of this thing, we just set our limits, set x limits. We just provide the lower and the upper boundary, which is from 0 to, I don't know, 20. There's nothing really much beyond 20. So what we can see in frequency, so if it says 20 now here, that means hertz, cycles per second, then we can see that in this case, the signal is composed of mostly by far the largest amplitude of waves that have a common frequency, namely 2.6 or something. And you can see it's the blue and the orange curve on top of each other. So both signals have the same frequency. And for the specialists, you might even see that there's a little bit more structure, that there's a couple of small mountainous regions, hilly regions here around 6, 8, and 11 hertz. And these are, in technical terminology, these are the harmonics. So they're just, the frequencies are multiples of that base frequency, which is, I don't know, is it 2.5, 2.7 maybe. So 2 points, 2.7 would be 5.4. So 5.4, you would expect the first harmonic, second harmonic, third harmonic. So we don't want to go into that. Just want to show you that once you have the grasp of time series, this is the most important and the first way to quantify time series in a perfectly justified way. One thing, if you want to know what is actually the main feature that distinguishes a time series from a normal data frame, it's actually in the order of the rows. Right? So if you haven't thought about it now, you know, of course, time, if we go back to our temporal plot, of course, it matters that one point, a certain frequency, say at the top here, is then followed by another that is smaller, another that is smaller, another that is even smaller. So the sequence of the rows, of the samples in the rows matters, which is not the case if you have a data frame where every row is a patient and then the, say, blood value of some hormone recorded as a function of patient. So every patient has a different value of that hormone that was recorded. So the sequence of rows doesn't matter. In this case, the sequence of rows matters. And so the important feature of time series is that they have temporal correlations or correlations along the rows. Right. So with that technical remark on this hot afternoon, I'd like to thank you for watching. And with this, I wish you a very hot and fruitful and productive Thursday afternoon, and hope you are back with us in September. Bye.